Hello and good day everyone. So in today's video, we would be discussing about the design of torsion reinforcement for reinforced concrete beams as per NSCP 2015 and ACI 318-14M. So when we say torsion, it basically means the twisting of an object due to an applied torque. And when we say torque, this is basically a moment. So from that guys, when we say torsion, it is basically a moment that would cause twisting of an object. So this image here is an example by Wikipedia and it actually depicts what torsion is. So as you can see, it is twisting. So in a structural engineering standpoint, it is often referred to as the moment about the longitudinal axis. So before I explain this, suppose that we have this particular beam here and say that we are now to apply this particular moment at the sides. So this is not torsion per se because as you can see that in this moment, its tendency is that it would be bending the beam like this. So from that guys, this is not a torsional moment. Rather, it is a bending moment. So suppose that I am now to rotate that figure in such a way that you would be seeing its transverse axis. So suppose that in this figure, I would be rotating it in this manner. So we have this particular, So suppose that we have this particular axis here. So this is now a transverse axis and this is also a transverse axis. So if we are now to apply a moment here about that axis, that is still a bending moment. It would just bend about its weak axis. And if we are now to apply a moment here, it would just bend about its stronger axis. So I will be introducing to you another axis, which is the longitudinal axis. And when we say longitudinal axis, that is the axis that is along the length of the member. So let me just erase all of my ink and rather I would just rotate our beam so that only the transverse axes are seen. So in this example here, the longitudinal axis is the axis that is actually towards us or away from us. And if we are now to apply a certain moment about the longitudinal axis, so this moment here, its tendency is that it would twist this particular beam in this manner. Okay? So that is torsion. So for the design of torsion reinforcements as per NSCP 2015 and ACI 318-14M, so same rules apply as with our previous lecture that in our design concept for USD, the required strength must be less than or equal to the design strength, meaning that the capacity must be greater than the demand. Okay? And from our previous meetings or in our previous lecture, we did say that for the required strength or for the demand, that is basically TU, PU, or even VU. But since we are to discuss about torsion, that we would now be discussing about letter T as in torsion. So torsion U or the ultimate torsion must be less than or equal to the design strength, which is reduction factor times the nominal strength. So take note that since the failure for torsion has similar failure with that of shear, it means that the value of P would still be the same as with the shear. And that is P must be equal to 0.75. Okay, so next question, do we really need to design our beams in torsion? So it actually depends. So hindi naman po laging nagde-design po tayo ng torsional bars or we are not always required that we would be designing all of the beams in torsion. So it actually would depend. So according to the code, according to code 409.5.4, if TU or if the ultimate torsion is less than phi times TTH, it shall be permitted it is actually permitted to neglect torsional effects. So meaning guys, if TU is less than TTH or phi TTH, you could actually neglect the torsional effects. So in other words, kahit wag ka na daw pong mag-design in torsion. But what is TTH in the first place? So when we say TTH guys, so I would be introducing to you two concepts such as cracking torsion and threshold torsion. Okay, so for threshold torsion, what does this mean? So when we say threshold torsion, this is actually referred to or defined as the maximum torsion that does not affect the member strength. So in Tagalog, itong threshold torsion daw is yung torsion na kung saan parang hindi pa ramdam ng beam mo. So that is now for the threshold torsion. And for the cracking torsion, this is now the torsion required in order for it to crack the member already. So once again, when we say threshold torsion is the maximum torsion that does not affect the member or parang hindi pa ramdam ng beam mo. And when we say cracking torsion, that is now the torsion that would cause cracking. So as you can see that in their formulas, there is actually a similarity here. So for the variables, they have the same variables, but the only difference of them is this factor here. So this is 0.33 and this is 0.083. So from that, guys, we could say from their factors that the threshold torsion, TTH, is actually equal to just the cracking torsion divided by 4, or cracking torsion is equal to 4 times the threshold. So in order for me to prove that, so looking at the calculator to your left, so if I am now to divide 0.33 divided by 4, that is basically 0.0825 or 0.083. And if we would now be multiplying 0.083 by 4, that is basically 0.033, I should say. Okay, so once again, these are their definitions. And if we really want to know if we really need to design our beams in torsion, this is now our basis. Once again, if the ultimate moment is less than P times the threshold, where P is equal to 0.75, and TTH is given by this equation here. So if it is less than, if TU is less than PTTH, then meaning that we do not really need to design torsion reinforcements. Okay, since once again, hindi nga po ramdam ng beam natin yung torsion kapag masyado po siyang mababa. But if it is greater, so if TU is now greater than PTTH, so we now need to design the torsion reinforcement. So for the design of torsion reinforcement, take note that so the longitudinal and transverse reinforcements required for torsion shall be added to the required VU, MU, and PU. So meaning that, for example, for your SRB, you have designed 4 rebars only. Then according to, let's say, your torsional design, you have solved for 2 rebars. So meaning that you would be adding those 4 plus 2. So meaning that you need 6. So same is true with shear or for the stirrups itself. If, for example, that for the stirrups, you have designed something, or let's say that you have designed the spacing of the stirrups 50 mm, for example, and let's say that you have also designed it in torsion, then you must take into consideration the spacing for torsion and for stirrups. So we would be discussing about that further down the line. Okay, so before proceeding, let me just go back to our previous figure from the design of shear reinforcement. So this is now a figure that I have gotten from the internet. So we have the longitudinal bars, and we also have the shear reinforcement, which we call stirrups or ties. So which of these steel members resist torsion? So short answer to that is that both the longitudinal bars, which is the main bars or which are the main bars, and the secondary bars, which are the transverse bars, would resist torsion. So ibig sabihin, dalawa po sila. Stirrups and main bars, they would resist torsion. So from that, guys, for our lecture, I would say that when we are designing torsion or torsion reinforcement, we would be designing the lateral. So lateral bars, no, not lateral. Sorry. We would be solving for the transverse bars and for the longitudinal bars. But let us solve for it part by part. And for the first, or for our first topic, we would focus first on the transverse bars. So for transverse bars, those are our lateral ties or our stirrups, okay? So it is said here in this slide that if torsional reinforcement is required, minimum transverse reinforcement, AV plus 280 minimum over S, shall be greater of the equations. So as you can see in this equations here, they are very similar to our AV min before, which is this. So ito lang po, parehas po siya dito for AV min. So basically in that slide, so where is that slide once again? For that slide, so yan, parehas lang po sila ng AV min. Okay? So how can we solve for the transverse reinforcement for torsion rebars? Once again, our main concept is that TU must be less than or equal to phi Tn, or we could just equate them. TU is now equal to phi Tn. So you're already given the value of TU and you already know the value of phi. You can now solve for Tn. Then upon solving for Tn, we have these equations here. So for the value of Tn, Tn must be the less than this one or this one. So for the first equation at the top, Tn is equal to 2 times AO times AT times FYT divided by S times cotangent theta. So if you are solving for the spacing or for the required spacing for stirrups for the torsion, then we would now be making use of this equation. Why? Because this is the only equation that has S on it. So if you are solving for the spacing, then you would now be making use of that equation. Okay, so what are these variables? When we say AT, so let's go to AT first. When we say A sub T, this is the area of one leg of a closed stirrup. So take note that we are only to solve for one leg here. So unlike in our previous lecture in shear reinforcement, so in this example here we have two legs. So for example that we have two legs, and if we have two legs, we would be multiplying the area of the rebar by 2. That was before. But for AT, we are only to assume that only one leg will be helping in torsion, because that is actually the case in torsion. So again, for AT, that is the area of one leg. Okay, so what about for FYT? FYT is the yield strength of the transverse bars. And when we say AO, guys, when we say AO, according to NSCP, it is actually said in NSCP that it is permitted to use AO equal to 85% of AOH. Again, that is permitted. But if you have a more specific solution in order for you to solve for AO, then better use that. But once again, according to NSCP, we are permitted to make use of this value. And what is AOH? When we say AOH, that is the closed area of the center line of the outermost closed stirrup. So what that means is that in this figure, suppose that these are now our stirrups, we would now be pinpointing their centers. So we would be traveling through the center of the closed stirrup, and from that, this is now to be it. So suppose that the boundaries of this orange box here, if this is orange or brown, or I would say that this is orange, if their boundary if its boundaries are on the center line of the stirrups, get that figure and just get the area, and that is already AOH. Okay, so that is now for AOH, and the main use of AOH is in order for us to get the value of AO. So there. Okay, so what about for the value of cotangent theta? So for cotangent theta, let me just erase everything here. So for cotangent theta is basically 1 over tangent theta. Let me just erase this. So once again, when we say cotangent theta, that is basically 1 over tangent theta. Whereas according to our provision here, theta is equal to 30 to 60 degrees. Okay? So if you are now to design non-pre-stressed beams, so for non-pre-stressed beams, theta is actually equal to 45 degrees. Okay? So theta is equal to 45 degrees for non-pre-stressed members. So non-pre-stressed. members. Okay, so looking at the calculator, if you are now to solve for 1 over tangent 45, so 1 over tangent 45, this is basically, so I'm sorry, so let me just close this one here. So 1 over tangent 45, that is basically 1. So in our analysis for non-pre-stress members, this is basically 1. Okay, so there. So this equation here is for transverse reinforcements or stirrups. And this equation at the bottom is for our main bars or longitudinal. Since, as you can see here, we are now to solve for Fy. And when we say Fy, that is the yield strength of the main bars. And when we say AL here, this is AL by the way, AL is the area of the longitudinal torsional reinforcement. Okay. And for PH here, PH is the perimeter of the center line of the outermost closed stirrup. Meaning that in our orange line here, or in our orange square on the figure on the right, just get the perimeter of this orange box. So that is now PH. Okay. So going back to our previous equation, so since I forgot to explain what these parameters are, so let me erase some of this. So let me just erase this first. So as you can see guys, that in this formulas or in this formula, we have ACP, we also have PCP in our formula. So for the ACP, this is the area of the outermost section of our beam. And when you say PCP, that is now the perimeter of this area. So meaning guys, for example, that we have this figure here once again. So when we are solving for ACP, so once again, ACP not AOH, we are solving for the entire area. Take note that entire area, not just the effective depth, but the total area itself. Meaning, we are now to get the total depth, not just the effective depth. Okay? So, is there a difference between ACP and AG? So, actually, there is. Suppose that we have a hollow section. When we say hollow section, yung butas po siya, we have a hole inside. So, for example, that this is a hollow section. If we are now to solve for gross sectional area for concrete, AG is just this part here. So, area of concrete only. But when we say ACP, regardless if it has a hole in it or not, so suppose that I would be erasing this first. So once again, if we would be having a hole in here, for the value of ACP, suppose that this is BW and this is H, this is still B sub W and, times H, I should say. Okay? So that is ACP. So regardless if it has a hole or not, ACP would still be the same. But for AG, you're only getting the area of concrete. So this hole here should not be taken into consideration in the area. Okay. So again, for PCP, for this figure, just add this side, plus this side, plus this side, and plus this side. Okay. So, and for the maximum spacing for our torsional reinforcement or for our transverse torsional reinforcement, is given by these limits, pH over 8 or 300 mm. So when you say pH over 8, this is 1/8 of the perimeter of the center line of the outermost closed stirrup. So once again, that is basically this perimeter here. So 1/8 of that. So that is now S max. Okay. So we would be having another limit here, which is the cross-sectional limit. So this is our basis if, let's say, your cross-sectional dimensions is enough. Okay, so for solid sections, you must satisfy this equation here. So we have here the shear, we have here TU, we have here VC, BWD, 0.626 square root of F prime C, and the like. Okay, so you must, of course, satisfy this equation in order for you to know if the section that you are analyzing is enough for torsion. Okay, so rundown. So when we are to design torsional reinforcement, the first thing that you should do, of course, is to solve for TU via mechanics of deformable bodies or even structural theory. So if you have already solved for TU, you can now solve for TTH using this equation here. So once again, the main use of this equation is in order for you to know if you really need to design torsion or not. So if the value of TU is less than this value, then meaning that you are not required to design torsional bars. But if it is higher than the threshold, then you are now required to design for torsional rebars. And for the torsional bars, we have two types. We have the transverse and we also have the longitudinal. So once again, in our video, we would be focusing on transverse first, or for the stirrups or lateral ties first. And take note that we need to satisfy this AV min. Okay, so later on that. So in order for us to solve for the transverse reinforcement for torsion, what we would be doing is that we would be solving for the value of Tn using this equation. And if you already know the value of Tn, you would now be making use of this equation here in order for you to solve for the spacing. So upon solving for the spacing, compare it with the S-max, and choose whichever will govern. And if you already have the spacing for both torsion and let's say you have already solved for the spacing in shear reinforcement, then we would now be combining them. So from that, guys, for AV plus 280, so take note, guys, that this equation is only for two lengths of stirrups. So we are actually solving for this S here. Ito po yung effective na po. Ito na po yung gagamitin natin sa site. And this is equal to AV over S. Again, this is for shear. So in order for you to solve for the effective spacing, you must first know how to solve for the spacing for the shear. Okay, so from that, AV over S plus 280, or this is now the area of transverse or of torsion, I should say. Sorry. So this is now the area of the torsion divided by the spacing that you have solved for torsion. Okay? So you already know this value, and you must be solving for this particular value for the effective. So with that, guys, again, you must solve for shear first, then torsion later, then combine their spacings in order for you to get the required spacing. So in the next video, in the next video, we would now be solving for a sample problem.